Hi, this presentation is going to revisit perspective and how it interacts with interpolation and screen coordinates. You can find this in section 2.4.2 through 2.4.4. I also touch on some topics from later on, the interpolation from 3.3 and hyperbolic interpolation from 5.5. But this is not exactly the way it's presented in the book either. I'm trying to give a more intuitive approach here to what's going on, just to set the overall picture of why we're doing things the way we're doing. In particular, why are we using the pseudo-distance? So the topics I want to sort of touch on in this presentation are why use pseudo-distance of z for depth values. And recall that pseudo-distance was a plus b over z for suitable constants a and b. So that was the first question to look at, and the second one is how interpolation works in screen coordinates. And again, I'm not going to get into the mathematics of this very much here, but just stick to the higher level, more intuitive approach here. So let's start with the overall picture of how a view frustum maps to the 2x2x2 cube of screen coordinates. So to recreate a picture from the last couple lectures but in a different form, let me draw the x-axis here. The z-axis is pointing down, so it's a top view of the xz plane. And there's a viewer sitting at the origin. And this is the camera or the viewer. Again, draw as a sort of stylized eye. And there's a view frustum sitting, should really be pointing right at the eye here, so it's like so this is the frustum that the viewer sees. And inside here, maybe there's 2 points, U1 and U2. And these things have, so U1 is going to have coordinates x1, y1, z1. And U2 is going to have coordinates x2, y2, z2. And we were projecting these onto the screen with this mapping that mapped us down to U1 prime and U2 prime. Now U1 prime and U2 prime had some interesting form because we had some choices on the z values. So U1 prime was x1 prime, y1 prime, z1 prime, and U2 prime was x2 prime, y2 prime, z2 prime. And I've drawn it here in the picture with z1 and z2 equal to the front z value here. So let's suppose this is z equals minus n. We used z equals minus d in one of the earlier lectures, but now n for the near clipping plane. And the formulas here was that x1 prime is minus n x1 over z1, y1 prime is minus n y1 over z1. These are the same formulas we had before, just with n instead of d for the distance. And then we had several choices for z1 prime, which I'll just put here as a question mark. What should it equal? Right, because we had several choices. But let's set that aside for the moment. In the end, we ended up using the pseudo-distance. But set that aside for the moment. What happens with the perspective transformation, this gets mapped by this transformation to screen coordinates. So over here I'm going to have the screen, but I'm going to do a front view on the screen. So here's the screen, the monitor, where the image is being displayed. And so we have x equals minus 1 on the left-hand side, x equals 1 on the right-hand side, y equals minus 1 at the bottom, y equals 1 at the top. And somewhere on this screen, we've got the images. Here's u1 prime, and here's u2 prime. These are the points here that I drew on at the bottom of the picture, which is the front of the frustum closest to the viewer. And this drawing is a front view of the screen. So the x-axis goes this way, and the y-axis goes this way. And so the 2 points in R3 have been mapped into the screen, and these have depth values associated with them. So U1 and U2 have depth values and other vertex attributes. So U1 has a depth value, and the depth value is the same thing as Z1 prime. U2 has a depth value Z2 prime. And these are the things I left unspecified how to compute them a moment ago here. They also have vertex attributes. And has vertex attributes. For instance, it might have color, it might have texture coordinates, and so on. So in particular, let's say might have C for color, C1 for color, and likewise U2 has a color, C2. Just for example, I'm using color here. And this is similar to what we did in the tent project, where we gave vertices colors, and then those are averaged across. And in screen space, when we're drawing things, OpenGL takes two vertices, maybe these are defining one edge of a triangle, and fills in the line between the two vertices with pixels that are colored. And because of the, strictly speaking, these are little rows of, say, pixels with jaggies from aliasing and so on. But we're just going to pretty much ignore that for the current talk and just assume there's a line going straight from pixel at position U1 prime to the pixel at position U2 prime. And the X and Y coordinates give you the positions of the pixels and the screen coordinates. And the idea, so what's needed there is that OpenGL is given the X prime and Y prime values for U1 and U2, giving you the pixel position on the screen. And then it also gets the depth value, Z1 prime and Z2 prime, and it also get color values, which are just copied over directly from the color values associated with U1, U2, and R3. And the question is, it uses averaging. Suppose we have some pixel in the middle. So here there's some point in the middle. I'll just call it V, right? So V lies on the line from U1 to U2, and it needs to also get depth values and other attributes such as color. So V on the line from U1 to U2 needs a depth value and maybe needs a color value, for instance, just for example. CV, right? And how is OpenGL going to do this? This is done automatically for you by averaging the colors and the depth from U1 prime and U2 prime to get the intermediate values. So let me talk more about this averaging process on the next board. So the difficulty with the averaging process is that values may vary non-linearly along the line. We've got the line from U1 prime to U2 prime. We've got a starting color, say, and an ending color. It may, in general, will not be a linear rate of change in the color if you're trying to be physically correct. So let me describe that. So here's the setup. I'll draw the screen again. So this is a front view of the screen. So we've got on the screen, we've got 2 points, U1 and U2. U1 prime and U2 prime. And we draw the straight line segment between them. And let's suppose the length of this segment is L. And we may go fraction alpha of the way, so let alpha be in the interval 0, 1. We may go fraction alpha of the way from U1 towards U2. So this is distance alpha times L. And this is distance 1 minus alpha times L. And here's a vertex V in the middle. More or less the middle. Actually, not the true middle. It's alpha the way across. So you might try, suppose that there's color 1 here and color 2 here. So the question would be, color V is what? Right. Well, what you could do is certainly could try linear interpolation. And what linear interpolation would do, this is sort of linear averaging, what linear interpolation would do is would set CV to be, we'd think of starting at the value C1 and then going alpha of the way towards the value C2. So the change in the color from C1 to C2 is C2 minus C1. So we take alpha times the change plus the starting color. And that's also the same as 1 minus alpha times C1 plus alpha times C2. And when we get to chapter 5, we'll see this is just the ordinary linear interpolation formula. But this was just a try it. The trouble is, this doesn't give the correct results. And maybe that even needs an exclamation mark here. And what we have to do instead we will use something that I'm not going to describe in this lecture. We'll use something called hyperbolic interpolation. And this is something we'll do later in chapter 5.5, section 5.5 of the book. But for now, I just want to say, why doesn't this give this? So why not, right? It's sort of amazing. To see why not, let's try drawing a picture of the view again in R3. So here I've got the x-axis and the z-axis. This is our top view again of R3. And let me draw the points U1 and U2 in somewhat different configuration. First of all, the viewer is at the origin. And maybe the point U1 is sitting here, and the point U2 is sitting here. And we can think of in R3 drawing the line between U1 and U2. And let's try, suppose this has color 1 at one end and this has color 2 at the other end. Let's try splitting this up into 4 equal segments. So here's 1/4 of the way from U1 to U2, 1/2 of the way, 3/4 of the way, all the way from U1 to U2. And then we draw the straight line segments to where these things, let's make this the, here's the line z equals minus n, or minus d, whichever you prefer. We're using this as our view screen distance. If we project, using the projection transformation, these 4 segments onto the view screen, by going straight towards the eye, what you end up seeing is that the segment's width shrinks dramatically as we get further away from the viewer. So this segment, the quarter segment, is close to the viewer. It occupies a pretty big area on the view screen. The next quarter segment's the same length in R3, but it projects onto a smaller area of the view screen. The next one's the same length again in R3, but a yet smaller area on the view screen. And the final one is still the same length in R3, but still much smaller here. So the colors, we think of the colors very uniformly here. Colors vary linearly here in R3, but they vary non-linearly in the screen space, in screen coordinates. Because See, here's the middle color would be halfway between C1 and C2. It's way over to the side in screen space. It's much closer to this is the U2 prime than it is to the U1 prime. And so we can see then the colors here on the line as seen in the screen space don't vary at a uniform rate. They vary faster when you're getting close to the end of the line that's distant from the viewer, and slower when you're at the end of the line that's closer to the viewer. And you can have other cases too where the line passes in front of the viewer. So it's slow in the middle and fast at the ends. So you get a nonlinear rate of change in the colors, and that's what we're going to handle by hyperbolic interpolation in the future. Okay, but the hyperbolic interpolation, you need depth values to make it work. You actually need the pseudo-distance values to make it work. You need pseudo-distance depth values for this to work. So on the next board, I'll talk a little bit about how we interpolate pseudo-distance. So the nice thing about pseudo-distance is that we can use linear interpolation on pseudo-distance and everything will work out okay. So let's redraw the picture here. It's similar to the picture I just drew here already, but everything works out okay. So for pseudo-distance, linear interpolation works. So let me draw the picture of this. So here we've got the same kind of picture with a view frustum. So here's the x-axis, it's the top view again. So here's the z-axis pointing down. Here's the line z equals minus n, or minus d if you prefer. I'm not going to bother drawing the view frustum here, I'll just work directly with points. So here I've got, for instance, 2 points, U1 and U2. And so the viewer is at the origin. We project down to the points U2 prime and U1 prime. Well, this is actually, strictly speaking, these are not U2 prime and U1 prime. These are x1 prime, y1 prime minus n, and x2 prime, y2 prime minus n. And we're going to set z1 prime equals a plus b divided by z1 z2 prime equals a plus b divided by z2. And here's what does work out with linear interpolation. You've got the points here, x1 prime, y1 prime, and x2 prime, y2 prime. And we look at the midpoint here. This corresponds to the midpoint on the view screen. So right here is the midpoint. So on the view screen, we've got u1 prime, u2 prime, and right in the middle, there's a midpoint that I'll just call it u3 prime. So the point is, this is a straight line on the view screen. It's supposed to correspond to a straight edge in R3. So here's the corresponding edge in R3. And where is u3 on this thing? Well, here's x1, x3 prime, y3 prime minus n. And then we see where did that come from on the line. So here is U3. It's the point on the line segment from U1 to U2 that, by the perspective transformation, goes to the middle of the line segment mapped to, namely the middle of the line segment from U1 prime to U2 prime. Okay. Now you'll notice that U3 is not at the middle of U1 and U2, not by a long shot. And so in particular, we have that Z3 is not equal to the average of Z1 and Z2. So linear interpolation would not work on ordinary Z values if you're trying to linear interpolate. But what we can do, what does turn out though, is that if we use pseudo-distance and we let Z3 prime be A plus B over Z3, where U3 is X3, Y3, Z3, then we do have that Z3 prime is equal to the average of Z1 prime and Z2 prime. In other words, equal to their sum over 2. And more generally, if you take a point fraction alpha of the way here, suppose this is 1 minus alpha times U1 prime plus alpha times U2 prime, you'll get again that if this is U alpha prime, I can call it here, then we're going to have that the Z alpha prime is going to be equal to 1 minus alpha times Z1 prime plus alpha times Z2 prime. So in other words, linear interpolation does work for pseudo-distance values. And this is why we use, one of the reasons why we can get away with using pseudo-distance. A plus B over Z. And it has the advantages of linear interpolation works. We can use a 4x4 matrix. And in fact, the reason that linear interpolation works is that we're using a 4x4 matrix. I'm not going to do the proof of this, but you can find it in the book, at least not in this presentation, maybe another one if someone asks for it. If you look at theorem 2.18 and corollary 2.19 on page 91 of the current version of the PDF file, there is a proof of this in a fairly abstract way that depends on properties of projective space. So linear interpolation works. We can use a 4x4 matrix. And then also pseudo-distance is exactly what we need to make hyperbolic interpolation work when we get to interpolating things like color and texture coordinates and so forth. All right, I hope this made some sense. It's a somewhat confusing concept to wrap your mind around, but I hope I've done enough to explain it. Thank you very much. That's the end of this presentation.